Okay, so more seriously calculate our necessary resources. This is the, I'm sorry, there's the parameters to use how much resource is necessary. So that based on this calculation, for example, rather simple calculation that the 1 year is, in this assumption, 7 million seconds. The trigger rate is 1 kilohertz. So that we accumulate 7 billion data, event data. So that in order to compare with the Monte Carlo simulation, we need some similar statistics of these simulation events. And then the storage size will be determined by the size of each event. Each event, for example, raw data, real experimental data needs 1 megabyte per event. And also, similarly, the simulation data needs 1. And also, we need also the CPU time to calculate. So that the biggest consumer is simulation. Full simulation is a very, very complicated process to simulate every step of particles and traveling inside the detector and so on. So that we need 3,500 hexspec 06 second. I'm sorry, it's HS 06. This must also jargon, but the spec benchmark for high energy physics. The fraction of integer operation and floating point relation is surveyed for the many high energy physics programs, and we determine the adequate fraction so that it's a measure how to evaluate the CPU power. Usually now one Intel core of the 2 or 2.5 gigahertz correspond to 10 hexspec. So that this means 3,500 means around 6 minutes of calculation for the one event or one core. And also the reconstruction needs some more, so that totally we need this amount of data. Gradually, year by year, gradually we need more data because the data are accumulated repeatedly. We have to analyze them. So that so that now we're reaching 4 mega HS06 that corresponds to 400,000 CPU cores, and also the 350 petabytes for all 4 experiments at the LHC. So how to implement this analysis system and how to realize this? In the idea is that we call it the worldwide LHC computing grid. So that the globally distributed data analysis infrastructure, they say that among 40 countries of 150 institutes, research institutes, including universities, and also implementing, I will show you that in a detail, somewhat detail on the implementation. This is the collaboration, WLCG. Now we have 42 countries, exactly speaking, 42 countries and 167 sites, one from Tokyo. But they are not the monolithic infrastructure, but there are United States, they have an open science grid. This is also the great infrastructure. And the Nordic countries are running their own one, Nord grid. And also other part, we are using essentially the EGI, the European grid infrastructure. The middle we are using, not the part of the organizationally, not part of this, but we are using the middleware provided by this activity. So why the distributed infrastructure is necessary? Of course, the sharing resource cost for such huge computing project is must be, of course, shared by countries, so that the sharing of cost is the main reason. But however, there are another reason that there are very large collaboration. Just as I said that from 40 countries, 3,000, even only for Atlas, we have 3,000 researchers. So these people should be able to access the data without a problem. So that this means that in a sense, to prevent the digital divide. So that it's the important point is in a sense that guarantee all equal accessibility to data for all the people joined. So that this is also important point. So that this system should be, of course, implemented on the network. So that the network is a key component, one of the key components. So that you see the LHC1, first we started the LHC optical private network for the connecting the major big sites which had tape archivers. But after that, it's in a sense a layer one private network. But they're now moving to LHC1. LHC1 is the LHC open network environment of the layer 3 virtual network covering all the country on the almost all countries belonging to WLCG. It's for example, this is the mesh, the monitoring mesh of the latency, and the latency and the bandwidth always we are monitoring by using the Persona toolkit, and this information can be used for dynamic resource allocation. If the connectivity is getting worse, the job should not be there, for example. So that if in order to utilize our resources, this kind of monitoring is very important. So that on top of this network, we need to implement there are very many services. I cannot explain all of these, but there are so many service. Basically, this in the elemental one is a global toolkit or a virtual data toolkit, or the ARC from the Nordic countries, or and the EMI, European Middleware Initiative, is the middleware service from EGI. And also on top, there are so many components, and based on these functionalities, we built our own production system, a data management system. And for example, our Atlas data distributed data management has a nickname on Lucio, but they are very complicated structure. But essentially, the storage is there are but very many kinds of data, including catalog, file catalog, and the history of access, or for example, the metadata belong to that data file set. For example, and so on. So that but actually it's working. Let's say the plot of the, for example, 1 year monitoring plots of the number of file transfer the previous year. So every time this line, the 100 million files per week. And so this blue line indicates 40 petabytes per week. So that's how huge data are transferred. And also this part is the storage space we are managing now. And they're starting from the 2008 or something. They increase and gradually they're now reaching 350 petabytes. And this is only for Atlas, so that they are including other experiments. And now the total amount is reaching, as in my title, the Exabyte is in the scope. So that workload management is also the another very important function that it's just a job scheduler or something like that. So that this is also not very complicated, but it's working. And so you see always this blue line indicates this diagram is also the previous year, and always 300,000 jobs are running at the concurrently. And it's our achievement, and this is the increase of the CPU resources attached to the WLCG. Okay, so that a bit let me advertise our contribution to Tokyo's contribution. The site name is Tokyo Research that operational since 2006, and we have these resources at the 10th floor of the science building on the Hongo campus. And someone said that the highest elevation of the computers. Why do you place such heavy computers at the 10th floor? Anyway, that there are this increase, our resources are also increasing. But one concern might be the network connectivity from Tokyo to the other worlds. It's also a very important factor. But now the situation is quite nice. That the SciNet is providing now the 100 Gbps connection to Pacific Los Angeles, and also the 20 Gbps to Europe, London, via Siberia. And also now the JGN, thanks to JGN, their connectivity connection to the Hong Kong is now upgraded to 100 Gbps, and also backup 10 gig to Manhattan Landing. So that in this situation, we are transferring data very smoothly. That this indicates the 1 year history of the previous year. The vertical axis shows that the transfer volume of the transfer speed of the 1 day average. So that even 1 day average, it hits 800 megabytes. So that's almost always blank field. So that, and this is the history of the SciNet of international connection in US. We started the planning of our system at around this year 2000 or something. At the time, the connectivity was less than 1 gigabps. But now we have 100. So that the situation is such good. Okay, but the computing demand is strong, still evolving, increasing. So that we have to expand our wings to new resources. One is the cloud computing. This already there a bit old chart, but we have many cloud computing centers. Someone in the private cloud based on the OpenStack or other middleware. And the other is the commercial cloud, just like Google or Amazon, but they are usually opportunistic. Not always we can use, but they sometimes with the collaboration with such companies we can introduce. Then this is the amount of the jobs are running on clouds. And also now the high performance computing is now our friends. So that in US, for example, there are many supercomputers involved in the WLCG framework, but there are some limitation. One is mainly for Monte Carlo simulation because of the data, so that the poor connectivity to outside, so that we need, because the main Monte Carlo simulation is mainly computing, so that the less I/O demand, so that this is adequate. And also, not always we can use but we use the high performance HPC in a backfill form as a workflow. We developed a workflow, distributed the jobs to idling nodes. And once the scheduler said that this must be our task must be purged, immediately stop the job. But there are no loss on the calculation because we are calculating every event by event. So that the efficiency is quite nice for now. So that finally this our production, the CPU clock time consumption, the grid is now less than 80%. High performance computing is more than 10%, and the cloud is around 6%. So the fraction is the fraction of this part is now increasing. And then this is also an interesting approach of the Atlas at home, the volunteer computing, connecting your desktop or any home computers to the. But of course, it's based on the framework, based on the Boeing developed at the Berkeley. But thanks to the virtualization, the stability is quite now quite very nice. So that even such computing resources we can run our simulation. So that in this snapshot, but 5% of the simulation. Of course, just I say that it's not adequate to transfer big data, but for the small data transfer, it's quite nice, and the 5% contribution is there now seen. I'm sorry about that. Okay, so that we are now we are after the 10 years of preparation. During this time, we have a very many improvement of the device, the system, and we performed run one without major problems, and then stop 2 years, and then start the run two 3 years ago. Since then, we are working well. Unfortunately, I have not enough time to skip this one. So the last topic is how, okay, skip this. Exabyte, why need? So physicists, the wish is to, one is precisely determine the property of Higgs. So that what we want to do is, we want to measure this peak under the background of this 5 order. So that in order to do that, a very high luminosity is necessary. So that our plan is to increase the accelerator luminosity towards the 2017 to 18, 2028 or 29, 10 times more from this early stage of the experiment. But the luminosity is 10 times more, so that already I experienced several times that 10 times more data is necessary. Event should be recorded. And also, each event becomes more complex, 100 times more complex. It looks like this. So that the size of the event becomes bigger, and also the CPU time to analyze this increases so much. So that now we have the blue dot indicates the resources, what we need using our existing system. So that we need, for example, CPU resource of a hex spec of something on the petabytes, the 5 exabytes of the disk storage. But you have only the limited budget. And so the flat budget model is assumed. For the 20 years, the budget is, now in Japan, they are reducing, but they are at least keeping the same flat budget. Even it can give only this rise, indicated by the black line. So that how to fill this discrepancy is a very, very headache for us. So that already Moore's law, you know that the Moore's law still work or not? Probably not. And that the clock speed is already saturated. So that but it is still a bit, the number of transistors increasing, so it's going to more CPU cores in the processor. So that how to utilize this is very important. And also the memory prices looks hitting bottom in this last 5 years, so that it's also crucial. But there's still, network is growing. There's ES network volume, traffic volume. This shows that now it is 77 petabytes last month. That it means that 30 gigabytes per second sustainable. So that's a very huge network connectivity. But at 10 times the increase, we are seeing 10 times increase every 4.5. And so that is some kind of the network is important. But also some machine learning also is very good. Must help us. So that our Turing system is so complex, but the machine learning can do much smarter way. So that we are started. For example, this is an example of for example, identify the objects is similar that for the high energy physics events and the car traffic or phase to the pattern of the calorimeter. So that this kind of must be good. So that the final diagram that I showed is a possible model for future computing. Now is approaching the HEP data cloud, that I say that the data and the computing is distributed around the world with a very high bandwidth network expected to be 10 terabits or something. But we need some evolution. Might be something like a HEP data lake or something. Data lake might be probably become a buzzword in a couple coming years. Okay, let me summarize my talk. That after 10 years of preparation, our computing ring started operation, and they are involving 40 countries and 150 institutes. It's a really big collaboration and contributed to the discovery of Higgs particles. And then after the 10 years of operation experience, now we can have a more stable and robust and flexible, automatic, user-friendly. But and expanding the computing resource for new ones like the cloud computing or HPC and even frontier computing. So, but our challenge is still on ahead. That the 100 times more data we have to manage. The linear extrapolation does not work. So, your suggestion is very, very well. This is what I want to say in this talk. Thank you very much for your attention. That's what.
Very much.